has issues with Clash Royale.
I'm addicted.
Yeah.
He chat like me.
Okay, so
We
while
also
we
had his
talked
phone
about
for 2 hours.
instantaneous velocity last time, most of the time, you have to know what it is. But as I said, you're not going to be calculating derivatives in this class. So you're going to be using average values, calculations that we do. But also, I guess it depends on who you take what professional, and you also have to be able to interpret different graphs. So it's like what we were looking at as a position versus time graph. We call that position versus time. So let's just put a curve in here.
No.
Yeah, that's supposed to keep that flat. Okay, so could you interpret what's, so if you had this on a standardized test, could you interpret what's happening on this graph?
Activation energy.
No.
It's giving biochem.
That's what it looks like.
That's all in our mind right now.
Yeah, no, literally.
But if you want to
like read
lecture on
biochem.
transition state theory and activated complexes, we could do that.
That energy on it. You don't need this sticking in.
No, only if it's Gibbs energy.
I'm just here to pass them.
Yeah.
Don't need this.
But,
Same.
So you have position versus time. I mean, we can do the math on transition state theory. I don't think you'll like it. I don't think you'll like it, but we can do it.
All I know is the symbol for transition state. That's all you get from it.
Yeah. So that first part that's flat, what's happening there?
That
Same
rest.
position. So zero what?
Starting energy.
But as you notice, as it starts to go up, velocity is going to become let's say up is positive. So you're going to be getting a velocity in a certain direction. So your position is still changing with time. However, your position is changing quite a bit in a little bit of time, so it's a high velocity. At the top, every graph is going to have a turnaround point. But that turnaround point velocity is what? Zero again. And so then, of course, as you go down the slope, you start getting velocity going in the other direction. It's like imagine you're walking towards that wall, then you stop and you turn around and you come back. Or if you change this, like the position of Y, imagine you toss a ball in the air, it reaches its apex, it stops momentarily, then it starts going back down. So make sure you look at graphs like this so you can understand what's going on with them. Okay. So we can find displacement with constant velocity. Okay, so here you see we have, you can have your different directions, your X and your Y direction, your change in X or change in Y is your position, your velocity in either direction, your change in time. You have your generalized, or you can have your generalized vector for X and Y. Because what we think, what's the definition of average velocity? Yeah, it's the rate of change of displacement. And so, of course, you remember so it's pretty easy to see where these three equations come from. What we're working up to is something called Newton's kinematics. So you'll see them as we go along. So let's look at finding our displacement.
Wait, can you go back up? I see the RY. Okay. Oh, RY. Okay, good.
Okay, at least you're not playing Word.
He's playing Clash Royale.
I told you were not supposed to give his phone back.
He said ethics, but I set a screen time limit for him.
Oh,
An hour
okay.
a day.
Help it. Not right now, but it will.
Haven't reached the hour yet.
Anyway, let's think about how we find displacement. So
A, B, C, D, E, F.
Again, some of this you get, some of it, like one of these you'll be able to use, one of them you won't. But at least you can see where things come from. So what? Let's say we have velocity in a certain direction, in time. Then we have a curve here. That's it's going to be a velocity versus time curve. Just we haven't talked about it yet, but if your velocity is increasing over time, what do you have? Acceleration. So one of the things you notice is if we look at this entire graph here, this entire curve, we have an initial time and a final time. So one thing we can do is, so if you want to know your position based off your velocity versus time graph, your average position, what you need is the area under the curve. So what's one of the ways we can do that? Yep, we're gonna get there. So the first thing we can look at it as is all of these little rectangles underneath the curve. So now you notice it's at a constant velocity. And it has a beginning and an end time. So if you wanted the area under that curve, what? Oh, time initial, time final. So again, if you do a sum of all those little rectangles, you're going to get an approximation for your change of position. Now, why did I do velocity times delta t?
Because delta t is the width.
Right, delta t is the width of the rectangle, velocity is the height. So remember your area, the area of each rectangle is going to be velocity times delta t. And so of course, that's where you end up with the equations you had above. If you remember, the change of position is going to be your velocity in time. However, these summations get quite tedious. But what we can do is imagine that, again, imagine that delta t gets smaller and smaller and smaller until it's pretty much like infinitely small. And that's your rectangle. And so what is the sum of a bunch of differentials? So again, a differential is going to be an infinitely small amount of time. You imagine you have almost an infinite amount of them under that curve. So you're really going to get an idea of the entire curve. So what is called, and again, something you won't end up using, but still, what is called yep.
Oh my gosh, integrals.
Bro. Oh, look, he's paying attention.
Again, hang on, it's not dx, it's d. So this is the more appropriate way to do it. I don't know why professional schools started saying that you didn't have to do calculus-based physics, because that used to be the way it is, but sure, but I can't make you solve integrals on homework or exams, but you're just going to see how we actually find this stuff. So of course your delta x, if you think about it.
You're making me cry.
I could if you want me to.
I really so easily could cry.
But I'm afraid if I make you cry just for the fun of it, I'm gonna mess up Brandon's Friday.
Real, you're a real one.
I just need to care about somebody in this class.
So.
Brandon, you're all red.
So I'm just saying, but your integral, of course, is going to give you your delta x because it's good, like you would end up covering the entire area under that curve.
I don't need to say.
No, we don't make our calculators do integrals. We learn how to do integrals. doing them.
Calculator do it.
No.
But if I had a calculator.
How about no? No.
How about a calculator that was $130
Learn to do the
doing?
math. We don't use the calculators, we don't use AI, because when we get to-
ChatGPT.
No, that's AI.
Chat is our friend.
Because when we get to our career in the future, we don't want our boss, our chief of medicine or whatever, to look at us and go, what is this? And you don't want to go, I don't know. Like, that's not a good thing.
I'm gonna ask ChatGPT how I do a surgery. How to do open heart surgery. Why is my patient crying?
Most people, because you didn't give them enough anesthesia. But most people in here, I would imagine, are joking with me. You know, I'm not so sure.
No, the ChatGPT is real.
No, he leaves whatever game that is. I don't know.
Cat lash royale.
Okay, so let's start talking about one of the more famous laws in physics, Newton's second law. So here you see one formulation of it, okay? Your change in velocity over your change in time, if we're going to get to that, is equal to 1 over the mass of your object multiplied by the net force. Okay, so that can be represented as, if you tell me you don't know what this symbol is, you're in trouble, because a lot of you saw it in chemistry.
I don't know what that symbol is.
Be quiet. The other one. I'll show you that.
That's just like what.
Or either do that one.
Yeah, Clash Royale is gonna get deleted on my phone. I hope you lose your game.
Or that one. You see the difference?
Yeah.
Okay, so that little mathematical symbol, what does it mean?
Proportion.
Proportional to.
Yeah,
So
I
the first
remember.
one, so when your open side is to the left, you read that as your delta V over delta T is proportional to the net force. The other way you can look at it is when your open end is to the right, that's inversely proportional to mass, or you could just write the proportional to 1 over mass. They both mean inversely proportional. So when something is proportional to another thing, what does it have to get an equal sign?
I don't like
No, it has to have a what? If I want to turn the proportionality sign into an equal sign, it has to have what? The proportionality constant.
I don't remember this from.
So like, for example, if I said A
There's so much going on.
is proportional to B, for A to equal B, I would have to have A equals some constant times B. That's proportionality.
What's the? Wait, what's the one for inverse? It's like the symbol.
Inversely proportional.
Oh, they flip.
Wait, that's what that fish is? Oh, I thought that was a large alpha sign. Me too, but don't worry. That's what they said about them.
Yeah,
Swim.
I thought that
you
was.
taught me, I was secretly signaling to all the Christians in the room.
They're united.
They're united.
No, that's a proportionality symbol.
But so it's not an alpha sign?
No, and it's not a fish.
The one that you underline is inverse.
Yeah, that's the inverse proportional. You can do inverse proportionality 2 ways. You either do the flip sign
Is it
or
like?
you do the 1 over whatever your value is.
Okay.
Could that be a capital Greek alpha?
It could be a lowercase alpha.
That's what I'm saying.
I don't know, man.
So.
That's capital, that's lowercase.
That's what I'm saying.
That's just A's.
Did you?
Check into my world. I broke him.
And is the-
Yes.
Teacher crying.
This isn't chemistry.
I looked up
feel
before
that.
class how to annoy my Physics professor,
You studied well.
You studied well.
studied that instead of biochem.
We've been,
Okay, so,
collecting intel since statistics.
so change in velocity. So remember your delta is gonna be a what? Okay. So let's look at this in two different ways. So let's say, let's look at this graphically. Let's say we have a initial
Let's tell
velocity.
her about your class royale during class.
The final velocity.
There you go.
Now, how would we represent delta V graphically? Yes,
Maybe it's the difference between them.
right. So we're gonna get the difference between them, but let's just do it graphically. So your delta V is gonna be that. Okay? But it's also a subtraction. So your velocities don't always have to be going in the same direction. Okay, so let's say we have an initial and a final velocity going in different directions. Your delta V, you remember, because when we were doing displacement, so your delta V is going to take the path of that subtraction between the two vectors. And since you notice, like, take the first one there, it's just linear. Your delta V shows that increase in velocity. So that means that delta V over delta T, or the temporal rate of change of velocity, is what? Acceleration. So again, remember, so now we have two rates of change. So you see the rate of change of velocity is acceleration. What was the rate of change of position? Oh, hang on, let me.
KP.
What was the rate of change of position?
They're talking about biochem. What?
If the rate of change of velocity is acceleration, what's the rate of change of position? Not speed, but the vector one. Velocity. So you see they're both rates of change. And then, of course, we take that original formulation of Newton's second law, and we take the m and we multiply it to the other side, and we end up with the one you see most of the time. Your net force equals the mass times your acceleration. I was going to show you the short derivation on this, but I think you get the point. Just remember that most of the time, this F.
Take this stupid from me.
So that F in the equation is your net force. Okay. So yeah, believe it or not, this is essentially the classical mechanics version of E equals mc squared.
Yeah.
You also start to understand that, for example, if you ever meet someone who uses radar guns and they don't have them calibrated, you'll get to inertial references, frames of reference. But if someone uses like radar guns and they don't calibrate them regularly, radar guns have to adjust for relativistic differences.
Like how much gravity?
No, like for example, inertial reference frames. Like let's say we both start out on the floor. You walk away from me at 2 meters per second. I walk away from you at 2 meters per second. How fast do you view me walking away from you? 4 meters per second. So that's the thing, the 4 meters per second isn't actually true because you're also your frame of reference is also moving.
Yeah.
So just like we had before, we also have instantaneous acceleration. So again, I put this up here, and of course you can see you have your average acceleration, which is your vector your subtraction of your final and initial vectors, your velocities. Your average acceleration then can be broken into the x and y components. And of course, you have your instantaneous acceleration, which we're not going to be using because, of course, it's another temporal derivative. That's one of the things that gets you when you get to quantum mechanics. You start doing the math and you realize that the spatial and temporal components can be separated into two different spaces, which is like, then you start to, it's weird stuff.
Zero limit does not exist.
That's the most I know.
Well, I've heard that. Where's that from?
Mean Girls.
Oh, okay.
That's the most I know about this.
Okay.
If it's equal to 0.
Yeah, it does not exist.
Like
Oh.
well, if you have a limit going to 0, and especially if 0 is in the denominator, there are formulations you have to use, but because of course dividing by 0 is how we get black holes.
I don't think you want to tell.
Oh, I do. I really do.
She'll hit you with a bus.
She'll push you in front of a bus.
Say push your brother.
You need to watch it.
That's about you.
Watch the originals.
Well, look at it this way. Look at it this way. I correct her, and either I don't get shoved in front of a bus, in which case I get to go home and have my Friday, or I do get shoved in front of, either way, problem solved.
Are we gonna like do like a test review or like?
No, what you want to look at, your exams are going to be things you've seen before. So if you look through the textbook, have you seen in the chapters, the examples that are worked out step by step? Your test questions could come from one of those with different numbers. It's the same process, or a homework problem you've done.
Okay.
But unlike on the homework problems, I make those so that they're going to take you time. I shorten down the work you have to do. So I take a homework problem and like cut it way down for a test problem.
Okay, sounds good. Is there like is this gonna be on the test at all?
No, not like, you've been doing the quizzes. You'll have like 4 questions like that. But then the rest of the others are going to be solve this, and it's either going to be an in-chapter example or a homework problem.
I want to be the bus.
Okay.
So if you just think about your quiz questions, and those are just like your basic concepts. Like, for example, if on, actually, yeah, this is a good thing to say, because the first year, my biology students made me readjust how I do exams. Because my first year I asked, give me the definition of Newton's second law. People were writing novellas. I got paragraphs, I'm like, no, F equals MA, that's it.
We did that?
No, not you, that was my physics class my first year. And someone wrote 3 paragraphs. And then apologized to me for their grammar, as if I know grammar.
That's really hard.
When I write my journal articles, I put them into Grammarly, and Grammarly's first response is usually, really?
My grandma is like,
So, I know our biology professors make you do grammar and spelling, and I don't, math, I do math. If you can give me a definition of something in an equation, you're probably gonna do okay. Okay, so,
I'm gonna give you the equation, but I'm gonna write the full word.
I promise you, I will take off extra points.
I feel like it's.
Okay, a person is sitting at a stop sign. Pull away from the stop sign, moving in, we'll just say the negative x direction. As they move, their speed gradually increases. I said I wasn't going to conflate those two, and then there I did. Whoops. First off, is this an equilibrium system?
No. Well, it
Why
starts
not?
in equilibrium, and then
Let's just think about after they start moving.
okay.
Why is it not equilibrium?
They're accelerating.
Right, so let's think about that. What does an equilibrium system have to be? If I do, what does an equilibrium system have to be? Sum of all forces is what? Zero. However, I have an acceleration. So that means for this system, the net force is not zero, so it cannot be an equilibrium system. Okay. So let's draw a diagram for the change in velocity, the acceleration, and the net force on the vehicle as it increases in velocity. Okay, so I'm just going to say negative x is that way. And so then I say, when they first start, they have an initial velocity. After a while, they're going to have a final velocity that's measured. Delta V looks like that. And so then the acceleration and the net force vectors, they don't have to be a certain size. You just have to tell me which way they're going. So which way is the acceleration going?
To the left, the negative x direction.
Acceleration, that, because you see how the velocity vector is getting bigger in the negative x direction? That's the direction of your acceleration. And which way would your net force go? Left. So that's all you have to do for this one. It's just kind of, it's understanding the diagram and what's actually occurring here. Because what would happen here? Deceleration. So in this time, acceleration is in that direction. Net force would also be in that direction. Okay. Here we go. So we have a boat that's sailing 6.17 meters per second directly east. A gust of wind forces the boat to change its direction to 11 degrees north of east and increase its speed to 7.2 meters per second. So first off, what is the magnitude and direction of the change in velocity of the sailboat in meters per second? If this velocity change occurs in 2.0 seconds, then the mass of the sailboat is 3,600 kilograms. What is the average net force and its magnitude on the sailboat during that interval? So let's start by kind of thinking about how this is working. Okay, so we'll say positive y is north, positive x is east. And then you have an initial velocity going to the east. Okay. Then you get hit by wind. You're gonna have a final. Methinks your exam today has made you lose your mind.
We haven't even taken it yet. We haven't even taken it. That's why we're
It's after this class.
Yeah.
Market sign up here.
It is 11 degrees, but let's think about what our system, so let's say, we know we're gonna have to do a change in velocity, so it's gonna be final minus initial. So let's draw this in a way that would look like a vector subtraction, and this one's just gonna be an initial estimate of what this is gonna look like. So I'm gonna put these both at the origin, is what I'm gonna do. Okay, so we'll just kind of draw it like this to start with. We want to draw it to scale, we may have to change it. But our vector subtraction goes from the head of the first one to the head of the second one. So we're going to need to find that delta V. Okay, so what we really want is we want two vectors here. The first one is easy. Your initial velocity is 6.17 meters per second I hat. You see why? Well, it tells you it's going due east, which means its entire motion is in what dimension? The X direction. So all you have is an I hat. So it's the entire magnitude in that direction. Now I need to figure out the final velocity. Let me guess you stayed up all night studying again?
I'm just tired.
You do know that at some point, if you don't rest, your brain does not produce the proteins to move short-term memory to long-term memory, right? And so then your short-term memory will start to light and you won't have the, yes, when you rest, your body produces proteins that will move the short-term memory to the long-term memory. Yes.
I think last night we.
I was like awake. I was awake. After they came and talked to me, I tried to sleep. I was just freaking back. And I just couldn't fall asleep. I don't even know what time.
She goes, are you awake?
I don't even know what time I fell asleep in Jana's bed.
And then I fell asleep after.
And then I woke up.
Sleep with your child anymore?
No, because I was up with them.
Yeah, maybe.
So of course, like we've been doing, we need to find the components of the final velocity vector. Okay, so okay, so we always want to start here. We always want to start with symbolic math before we start plugging in numbers. Already have some people trying to take shortcuts, knock it off.
Yes.
I can tell I'm getting some assignments, but it seems superfluous to write all this math, and you should put numbers in. No.
That's definitely.
I was gentle on the first two assignments with that. Don't do it again.
You bad.
You bad too.
Mine are all today. Mine are all right now.
Okay, so what do we have?
Every single one. Everything. I even got bonus points on this one because I wrote something different.
Yeah, that was really good. Okay, so we get a X component
No, I didn't.
from 7.07 meters per second I hat. What about our Y direction?
Look at my princess coloring book.
So when you use your calculator, you get 1.37 meters per second J hat. So you're going to get a final velocity vector.
You add those together and square
No, we do not.
it. No.
So-
Square them.
One thing I want to make sure we cover, because I've been seeing this on homework. So when you're doing when you're adding together vectors, so let's say we're adding force 1 and force 2. Okay, I saw this a couple of times. What I saw F1x plus F1y plus F2x plus F2y equals some number? No. I will get a newspaper if I have to. Remember, you add together your x's and you add together your y's. Those are two separate components. You cannot just add together all your x's and y's. What you have to have and those are going to give you components of a new vector. Do not add together your x's and y's. Okay, so now we know that we need to find delta V. V final minus the initial. So when I do that, V final x minus the initial x hat plus y, the initial y, j hat. And so then I start looking at my vectors. So the x component for my final velocity, 7.07 meters per second, minus your v initial only has an I hat, so you're going to subtract off 6.17. Okay, plus your v final y is 1.37 meters per second, and there is no y component for your initial vector. When you add all this up, what you're going to get, your delta v, (0.90 meters per second I hat, plus your 1.37 meters per second j hat. Now, if you want the magnitude of this change in velocity, now you do what you were talking about. You have to get your new vector first.
So much in my brain, I just need to throw it up on the test and get it.
That's going to give us 1.64 meters per second.
What?
So that is the magnitude of our change in velocity. And then the direction of our change in velocity. We're just going to use angle phi. And it's y over x.
This is so funny.
Phi is going to be 56.7 degrees. Now, if we go back, we'd have to adjust our original approximation of our vectors, because as you notice, this change of velocity has two positive components, which means it would have to go into the first quadrant or in that direction, and it would have to be 56.7 degrees counterclockwise from the positive x-axis. So our corrected so you have initial velocity, our final velocity.
What is angle for?
That's your final.
I'll show you. So remember here, we have theta. That's the angle you just found. That's your phi.
Oh, why do I care about this?
So that would be our corrected set of vectors based off the calculations that we did. Now, we've learned about velocity, we've learned about acceleration, we've learned the definition for Newton's second.
Can you go back up, please?
Where to?
Right there.
You're just. Yeah, our brains are
So-
literally not here.
Yeah, we've now learned Newton's 3 laws of motion. The first law, an object will stay in its state of motion unless acted on by an external force. That's the inertial law. Law 3 is, remember, we were dealing with interaction particles. Law 3 is equal and opposite reaction. Law 2 is the most famous one, the one you're going to use most of the time, is your F equals ma. Net force equals the mass of your object times multiplied by its acceleration. And in this case, we're talking about proportionality. Mass is your proportionality constant.
This picture's actually funny.
Yeah, that's good.
Okay. We can at least get this one
Beautiful
started.
Quizlet somebody.
So, person is dragging a suitcase.
It's in a wheelchair?
Dragging along the floor of the airport.
Huh.
I don't know why you don't carry your suitcases in the
That's
water,
big.
sir. It's probably this. The rope makes a 40-degree angle with horizontal.
I do remember the crown.
The suitcase has a mass of 36 kilograms. So eventually we're gonna figure out what force,
Can I get myself
with.
Sure you can, I'll use Get myself like that.
And the suitcase will have a kinetic friction coefficient of 0.13. So let's just start out by looking at the free body diagram for this.
This is a suitcase with a rope.
So we have the suitcase.
Summer a year ago.
Immediately we know
36 kilograms times gravitation, 36 times 9.8.
And what are we using now? What is weight equal?
Mass times
Mass times
gravitation.
gravity. That's your gravitational force. Okay, so now I also know the suitcase is moving, so it's going to have a, oh, not X. It's going to have a kinetic friction force.
Now I'm gonna laugh at you with your head on the
So I'm going to put in X in my components because then
With the rope.
Yes.
we're going to have a force that pulls a suitcase at an angle of 40 degrees. And so, of course, yeah, we could represent that as a tension, but the tension is going to equal the force, so we're just going to represent it as that. So on Monday, we'll continue from here and work on solving this problem.
I said none of us just.
Yeah, we're just gonna be using it now. Because we're really getting into motion, especially non-equilibrium systems where we have a mass times acceleration. So all your
Probably
forces
say, I'll just
together
get all
equal mass times acceleration. Everything we cover up through the end of Monday. Because some people are going out of town, so I'm gonna have the tests ready for them by Wednesday, so everything up through Monday will be in free game. So all of these ones that work out are supplementary questions that go along with your chapter examples. You want to make sure you're going through the chapters. There are in-chapter examples that are worked out step by step.
I don't wanna wear my sweatshirt outside, but it's.
Yes.
This is valid.
Yes. Okay, perfect. And then which chapter?
Don't speak.
I was like, whew.